pleasure to introduce my colleague, Professor Iryna Perova. She's professor of Biomedical Engineering Department at the National University of Radio Electronics. We have been working together for a while, and now she presents a lecture and then workshop afterwards. Instead of her colleague Iryna Perova, she hopefully does everything properly. So, developing deep auto-encoders model for medical data streamlining. Please enjoy.
Thank you very much, Alina. I really appreciate to be presented here to show all my results. And for today we have some agenda. And I want to tell you about feature selection and feature extraction tasks for medical data mining. Also, I want to tell something about autoencoder, what is this, and what is it used for. Then something about autoencoders types and application. So, first, feature selection and feature extraction tasks. Why we need to do it for medical data? As you know, medical data is a data that can be characterized by low number of objects. So we have not many patients to analyze. Yeah, but each patient has so many features, so many medical indicators. And I can say you that the number of indicators is almost equal to number of objects. So we should reduce our number of indicators by different methods. And this method is called like feature selection and feature extraction. What is the difference between them? So as you can see at this picture, feature selection, it's when we took some number of features and then we just drop some of them and leave all other. And then we make some, maybe supervised learning system or maybe unsupervised learning system. So it just reduces. By some ways, I will tell later about the ways. What is feature extractions? Feature extraction, it's like we have some features, then we have some actions with these features, and then we can obtain other features, for example, by other nature, other dimension, other axis for describing this picture. And this task is more complicated than other tasks, like feature selection, because feature selection is simple. We took this first, second, and for example, fifth feature, and that's all. So, why we need to do all this? A minimum feature extraction tasks is always needed, always, in all data sets. Because sometimes we measure, for example, a height of person in centimeters. Then we add some features, and this feature contain height of person in meters. So it will be some feature extraction. We change some feature to make from this feature one table, yeah, to measure this feature in one scale, one particular scale. Feature extraction tasks can be made inside deep learning system. It's like a part of deep learning system today. So we have no need to, in deep learning also, in deep learning, we have no need to build feature extraction system like a system, systems that is need only for these tasks. So we should build it inside deep learning. And for other tasks, not deep learning, we can build it but like a separate approach, or maybe some program, maybe some module in your system. And feature selection is applied when we need to reduce a number, and we have so much information to make it inside your system. It can be, for example, we can make it, for example, to avoid a curse of dimensionality phenomena when we have many features and little number of objects. So, how we can make it? For feature selection method, we have such maybe like workflow, maybe. It can be filtering. So, what does it mean, filtering? So, we can rank the original features according to their relationship with some labels of our data. For example, we know how our classification should be. And we see if we add to our filter only first, second, and third feature, our classification became better. So it's like filtering depending on our task. Also, we can make it by creating some model and creating potential set of our features. Then we train our model, we calibrate and repeat this process when we receive some optimal number of our features. It's also good. And also embedded. Embedded is method that can be based on machine learning techniques, and this procedure is included inside of our machine learning techniques at all. So it's like our model include like pre-processing stage that performs some feature selection method. What about feature extraction? You can see here, so feature extraction is more complicated action. So we have some features here. And then we find this, for example, this feature has invalid values. Some wrong formats, maybe some invalid values also. Some duplicates. For example, we can measure height, we can measure weight of our person, and we can calculate the combination of height and weight. Yeah, it's no medical parameter, so we have no need to use all this information in our data set. So it's like duplication of parameters. So at the stage of like data mining or maybe data analysis, we should find these features, and feature extraction system, these duplicates, it's really easy to find these duplicates and maybe to remove them, or maybe leave two features, or maybe leave only one. Then maybe your data set has some missing values. It's normal for medical data sets, so many gaps there. So we should understand what we should do with these missing values. Maybe we should fill in it. Maybe delete. It's like, it's your choice when you form your data set. Then maybe we should uncode categorical features. Maybe by this way, maybe by other. We should remove some outliers from our features. So you see, this step changes our data. They became other, yeah? And then we can make some steps like decomposition, aggregation, some combination of our features, and then this step can be done again and again, and then almost all systems contain the stage of normalization, and then we can make like our dimensionality reduction. It's our principal goal here, and we have such reduced number of features. Feature extraction method. Is it known system or not known system? In classical mathematical statistics, it's a really known method. And feature extraction method, like principal component analysis, it's known method of factor analysis. It was invented by Pearson in, you see the year, 1901. And again, it was like reinvented in 1933. The first use of this method was in 1954, so it's really old method. How we can describe this method? This picture from Hubble, it's a really good idea to describe principal component analysis. We can see here really not simple object, yeah, some object, but if we want, we have some task to reduce this dimensionality of this object. Here you can see like axis x, yeah, axis y, and axis z. Its object has three-dimensionality of our space. So how we can to reduce it? For example, I want to reduce by removing y. What it will be? So we can like see this picture from this point of view, and we see some sense of this picture, and the sense is no. Okay. In other case, if I want to reduce other, so it's like not feature extraction, it's a feature selection. Yeah? I want to get rid from x. So I should see this picture from this point of view. And the sense of this picture became yes. So what is good idea to reduce? Because we have, we can attain opposite points of view for this picture. When we try to understand the sense of this picture. How to do it? And PCA, or principal component analysis, help us to build from our table that has n objects, it's like our passions, yeah, and m variables, like our medical features, the table with p features, p variables, and p is less than m. So we can reduce number of these features. When we do it, we should balance between two problems. It's problem of easy understanding and clarity of representation. So we should like save the sense of these features. And then we should reduce number of features to make our future processing of this data better. So to make possible to find some classes, find some clusters, or what we will do with this data. So we should make it possible. Do not lose an important information from this data. How does it work? So, okay, we take our, a little bit number of formula here, so it's not about my lecture formula, it's not about my lecture, so it's only few of them. So, we have the matrix, n objects, m variables, and we want to create some system to describe this data. How we should describe it? The first understanding of describing, it's creating the first principal component that display the variation among our objects. So why variation? It's a principal question here. Because, for example, if our data doesn't change, is it information in this data? Are there or no? Maybe not, because if all people in this room have the same temperature, 36.6, it's not good feature. It's also feature, okay? But when somebody has temperature 38, the feature of temperature became the most, with the biggest informational sense, yeah? Because, oh, it's changed. So variation of our data, it's really important. So, okay, how we can represent a cloud of our data in feature space at what we should measure. about this cloud. We should measure two principal like variables. It's a centroid of our data. It's like mean of each variable. And variance, yeah, formula of variance, it's known formula, it's presented on this slide. Okay, maybe it will be good, but when we see these three clouds here, you know, all these three clouds has the same center and the same variance. It's like here you can see what is the center or the mean of our data. It's a central point of this cloud. So you can see here central point, it's like 0, 0, yeah? Here central point, it's also 0, 0. And here central point, it's also 0, 0. So 0, 0. It's like centered data. When our data are centered, they have a mean from 0, 0 point. Of course, here we have a cloud that is measured using two features. Here we have feature 1, and here we have feature 2. But when we are talking about some biggest number of features, so dimensionality of our space grows, and it's not 2 axes, it can be 5 axes. It's really complicated to imagine 5 axes because we are living in a 3-dimensional space, yeah? But from mathematical point of view, we can describe our object by numbers of features that can be presented like a feature space with some dimensionality. Okay, what about variance? We shouldn't calculate variance using those formula. We can almost see from this point to this point. It's like from -1 to from -9 to 9, and here you can see it's like -4, I think, to 4. Okay, these pictures, the same. These pictures, the same. And third picture also. But the data are different. But they have the same variance and mean. Maybe variance and mean, it's not enough to make understand what data we have. So, what we should calculate more to make our cloud, or to make understandable what cloud of data we have. You know, it's covariance. Covariance coefficient can be presented by this formula, and they from this coefficient we can build covariance matrix. Covariance matrix helps us to build special matrix of special type, where we have this matrix. Here, like in principal diagonal, we have variances of our data. And here we have the coefficient of correlation. And you know, if coefficient of correlation is has positive sign, we have like growing of this feature and growing of this feature. Yeah. If we have the sign before correlation coefficient minus, so the growing of this feature it lead to reducing this feature. So it's like opposite sides. So it helps us to build and to understand this coefficient, what is the cloud of our data. So then PCA measures the dimensions of this covariance matrix and build engine vector of which on which the maximum variance is projected. So our situation became like this. Here you have feature 1, here you have feature 1, here you have feature 2. And you, what the PCA do? It reduce or maybe rotate some our original variables to make first principal component the direction of first principal component like the direction of the biggest variance of our data. and other components are orthogonal to first component, and they build the new feature space. The physical sense of this component we don't know this physical sense, because in first principal component all features like make some coefficient and his value. So it's like combination of all features. Second principal component is also combination of all features. So our data became in other feature space without physical interpretation. There are so many methods to interpret what does it mean this principal component, what feature has the biggest influence to, for example, first principal component. But it's not about understanding, and there are no information there. You shouldn't use it. So this method is used for dimensionality reduction and also for visualization of our data. Today we will discuss how to build PCA using some little code in Python, so it will be in our workshop today. Okay, it's good. Feature extraction. Why we need auto-encoders? What is this auto-encoder? It's like a traditional architecture of neural networks that can be used to extract from complex, large-scale data that maybe some sense to extract, or maybe find some important information. So it's about feature extraction also, yes, it's the same. So how we can compare auto-encoders and PCA? This picture shows it, I think, in good manner. PCA, it's about linear compression, because this matrix, covariance matrix, it's about linear dependencies between data, yeah? At autoencoder, it can make some nonlinear manifolds of learning nonlinear manifolds inside your data, and to reduce the number of features better, because it's oriented not on linear model like PCA, but non-linear model depending on your data. Okay, you know, autoencoder model was introduced in 1986 in classic paper of Rumenhout, Hinton, and Williams. You can find it, you can see it in the picture. It's like chapter 8 from some book. And you can find it using this link. And today we have so many types, different types of autoencoder for any tasks, and we can use it like a part of deep learning system. And today I'll show you that you can use autoencoder for anomaly detection task without any additional systems, only using autoencoder. It's and you can use it for your data, tabular data, yeah, like I said before, and also for time series. Our workshop today, it's about time series, because it's really complicated to process time series, because you know, when you have some data, you can mix this data. First feature can be third feature, nothing changed. Yeah, it's about only feature. Yeah, when we're talking about time series, you can't mix time series, your time in time series, because if you change the first moment of time and second moment of time, it became other time series. You can't mix it. So it's really important, and we will discuss how to build this autoencoder for time series. What is this? Autoencoder, it's like this model, where we have some input information, and we have some reconstructed input information, like in reconstructed output. This model has part that is named like encoder and part decoder. Between them is a bottleneck. Encoder learns how to reduce input information or reduce the dimensions of input information to compress our data to some value, I think. For example, you can say, I want to find only 5 features from this data. And here, in bottleneck layer, you can find your compressed information that consists, for example, 5 features, if you want it. And then we have a part of decoder. This decoder learns how to reconstruct your data from these 5 features. So it's like reducing and then reconstructing our information. And this reconstruction loss is the most important thing. So you should find the best way. You should turn the parameter of auto-encoder to make this reconstruction loss close to 0, yeah? In ideal cases, we should obtain 0, so we can reconstruct without any problem, without any... Okay, and then, how to describe it mathematically? We have some encoder functions, it's like phi here, and we have some original data. And this function makes from our original data some reduced space of our data, so it's f. It's something that is inside bottleneck. And then decoder layer can build from our reduced data our original data. And we should find the minimum from between our encoder and our decoder. Okay, but autoencoders has also hyperparameters. So we should know how to compress our data, we should understand it, and we should tune these parameters. For example, code size, it's number of nodes in the middle layer. It can be different number, it depends on our tasks. And also we should maybe add or remove some layers. For example, our encoder can be built using 3 layers, or maybe 4, or maybe 5, or maybe only 1. How to decide? And also decoder layer also should be built by some specific number of layers. Number of nodes in code layer also we can change it to make our autoencoder better. And last function, it's about some function how we will calculate this loss. It can be, for example, mean squared error. Today we will use this reconstruction, this last function, and maybe it can be binary cross entropy. It depends on your desire, on you, like you build your autoencoder, so you can find some function for this. Okay, today we will talk about some autoencoder types, how we should find. It can be undercomplete autoencoder, denoising, sparse, contractive, variational, convolutional, and at the end it's a deep autoencoder, because about deep autoencoder will be our workshop. Let's start from beginning. Undercomplete autoencoder. You know, all this picture for you will be almost the same, because we have we have encoder level, we have decoder level. Here is bottleneck, it's input layer. Input layer, they almost the same, but some of these autoencoders have some particularity maybe inside, and this particularity divide them from different groups. Undercomplete autoencoder is the simplest architecture. It's about like from what we start. For constructing, we need to constrain the number of nodes in the hidden layer, here in bottleneck, And that's all. So, model learns the most important attributes of the input data and how to best reconstruct it to output data from uncoded state. There are no regularization terms here. It simply trains our model according to reconstruction laws. And that's all. And these autoencoders have some pros and some cons. What about pros? Do not need any regularization here. So they can be built by easy way, but some cons here. Over-parameterized model, and if we have not a lot training data, our result will be overfitting. So this autoencoder can't work properly clear. Okay, but it was the simplest architecture. Denoising autoencoder. You can see it here. Add input of our autoencoder, but not input. It's like this autoencoder creates some corrupted copy of our input information, corrupted by noise. So some noise added to our input information, and they became partially corrupted. While training, this autoencoder tried to reconstruct from noisy input denoised image, some denoised information. This model analyzes a vector field from lower dimensional input data to mapping it with corrupted data and cancel out added noise. Okay. You see, this autoencoder has a lot of pros. So it minimizes the loss function between output node and corrupted output. And this noise became a regularizer of this autoencoder. And it forced our autoencoder to study independent features from each other. So it finds in our input information the most important feature and can it present in bottleneck layer. We can make this corruption by noise by different ways. It can be random corruption of our data, or maybe, for example, we can make some features equal to 0. It's like missed information, yeah? It became our feature corrupted. But we can make it by different ways, and it helps to make from one data set bigger data set. Because you know, today we will discuss it, but for training autoencoder, we should have many training data. Because without training data, there are no autoencoder at all, because it's like, as you see from my lecture, autoencoder, it's close to perceptron, because it's also like all deep learning systems are close to perceptron, because they build from three plus layers, yeah? And these layers, for its training, like and autoencoder also, use backpropagation sometimes. It's like about perceptron. So, denoising autoencoder helps to make our training data bigger, to train better, but by adding noise by different ways. So, setting up of this autoencoder is easy. And what about cons? For training autoencoder to denoise our data, it's necessary to perform preliminary stochastic mapping in order to corrupt this data and use as input. this model isn't able to develop a mapping which memorizes the training data because our input and target output are no longer the same. So the noise changes it. That's why. Okay, the next type, variational. You see, all autoencoders became different because something is added inside your data. In the noise autoencoder, it was noise, like a regularizing parameter. Here, in variational autoencoders, we use some, for example, some law of distribution our data, or the law what we want to our data be distributed. It can be, for example, Gaussian law. It's possible. So the variational autoencoder models make strong assumptions concerning the distribution of latent variables. For this, variational autoencoder can use a different approach. And here we use special training algorithm called stochastic gradient variational Bayes estimator. It's special algorithm for variational autoencoders. Also, sorry. One of like its pros, it's the probability distribution of latent vector of a variant autoencoder typically matches that of the training data much closer than standard autoencoder. And also the process of them, it's this autoencoder gives significant control over how we want to model our latent distribution, unlike the other models. And after training, you can just sample from distribution followed by decoding and generating new data again. But this autoencoder use the techniques known as backpropagation. Backpropagation can lead to overfitting of our model. So it's in training process, you should have some extra attention because you need to calculate the relationship of each parameter in the network using these techniques. And sometimes it's really not easy to build and to train this model because of this. Sparse model. And again, you see the same picture, like encoder, decoder. What is the difference here? Sparse autoencoder, it's like the models that have in hidden layer number of nodes greater than input nodes. And you say, wow, we should reduce our information one way bigger. But it used like sparse techniques. So it's like not all neurons and not all nodes became activated. They activate only some of these nodes, not all. All other became frozen, it's like frozen, yeah, and their parameter doesn't change. And it's like in hidden layer, yeah. It prevents of copying our input information to output because we have so many nodes. We can copy it and that's all. All was done, yeah, it's okay. Reconstruction was perfect. And that because of this particularity, we can't, our autoencoder can be overfitted because of this. And we will use these techniques in our deep autoencoder when after each layer we will froze the part of neurons. It's like I think 20% of these neurons, to make our auto-encoder not be overlapped or not be overfit. So we can make this sparsity in our loss function during training process, or maybe by other way, by manually, maybe we can manually zero some neurons and the parameters became frozen. Process of these auto-encoders. You know, it's like a value became close to zero, but not a zero at all. So it's like because of this, we obtain not zero elements and it leads to not overfitting of our model. It's the principal goal of this. It's really good because you, as I said before, such types of autoencoders leads to overfitting. And also, this type of autoencoders take the highest activation value in the hidden layer and zero out the rest of the hidden nodes. This prevents autoencoder to use all the hidden nodes, so we shouldn't use because they have almost zero parameters, yeah? And we should find in hidden layer such information we want, but is this information not only in all these neurons on all these nodes, but only at part of them. But this autoencoder also consists, have some cons. For it, for this autoencoder to be working, it's essential that the individual nodes of the trained model, which activate data dependent, and that different input will result in activation of different nodes through the network. So our information, it's like hidden in hidden layer, so we should find it because we have so many neurons here and only a little part of them consists some information. The biggest part of this neuron are frozen. Okay, also contractive autoencoders, you see the same picture and what is the main idea of constructive autoencoders? It's about this autoencoder has a robust learned representation which is length sensitive to small variation of the data. So if our data change a little, this autoencoder thinks that we have previous data, so it can make maybe some classification. Here you see this idea is inside our autoencoder. For this autoencoder, use another localization techniques, not like sparse autoencoder where we hide some information hidden layer, not denoising because we doesn't add some noise, we doesn't add some variation, maybe some loss of distribution our data, not such information. These regularities correspond to the Frobenius norm of the Jacobian matrix. I don't want to add there some formulas because it's like you should understand only the sense, because the autoencoders that we will build today with you will be based sometimes sparsity. We will use these techniques. Also, we will use techniques about deep autoencoders. So I don't want to add there some formulas because we have no need to see formulas. And I know that you here, like you are representing some groups of researchers, like Nano group, yeah, from maybe some technical group like computer science, also other students, and it's really difficult to show some formulas and to see the X, Y. It's like maybe some guys didn't understand about what I said, and so. Why this norm? Because this norm for hidden layer is calculated with respect to input, and it's basically the sum or square of all elements you can see here. So it's a simple norm, and this contractive autoencoder, it's like a simple autoencoder. It has some process, it's like better choice than denoising autoencoder because nothing doesn't add to our data. But it's a really easy way to make some feature extraction. It's like not about reconstructing, finding some dependencies in reconstructing. It's only about reducing. And we can take from this autoencoder, from this layer, some reduced number of our features. This autoencoder is better to use for this. Okay. It's almost the end of our classification. I'm so sorry, but I should tell you about all we have in our autoencoders type. It's convolutional autoencoder. This autoencoder uses the convolution operators to exploit the fact that signal can be presented as a sum of different signals. It's like convolutional neural networks. Who knows, who worked with these networks, know it's about like a main principle of these networks. So the input is encoded as a set of simple signals. And then convolutional autoencoder tries to reconstruct the input from these simple signals. Here we have some layers. You see this autoencoder is close to deep because the number of layers, you can see 1, 2, 3. Here you can see some information and then reconstructing 1, 2, 3. As I will say a little bit later, deep autoencoders consist of 4, 5 layers, maybe 3 layers. In total, it should be more than 6 layers. It's like when we use some theoretical information about deep, it's like 6 layers and more. So we can say that convolutional autoencoder is something about deep autoencoder. Convolutional autoencoders are the state-of-art tools for unsupervised learning of convolutional filters and maybe some other neural networks. These autoencoders can be used like pre-training model or maybe like pre-processing layer for deep systems. Because right now we have like I don't know, it's like a fashion maybe in deep learning. We never use random parameters for our deep models, because when we start from random parameters, the tuning of our deep models became more complicated. Then we use some pre-trained system. So this autoencoder can be like pre-trained system for different types of deep systems. And for different tasks, you know, it's easy to find some pre-trained system in internet. It depends on your task. For example, for natural language processing, when you build some deep system, you should find some pre-trained autoencoders or maybe other neural networks, little part of them, and you can download it and use for your deep system. It make your system works better. Okay, about process. Due to this particular convolutional nature, the scale will to realistic sized high dimensional images. So you see, on all these pictures, as I show you, you see here picture, picture. Yeah, auto-encoders, the biggest part of them are used for some image processing, signal processing, video, but image and video is almost the same. Like video is a sequential number of images. Yeah. So yes, but today it was my goal to find some way to use autoencoder, not like a system for image processing, but also for data processing and for like time series processing. So, here we can find the cons of these autoencoders. It's like sometimes due to some loss in information during our encoding, we can make this our picture of lower quality due to this compression, because some information was lost. It's like if we use this autoencoder for image processing, it became our result. Our picture became worse than it was previously. And again, deep autoencoders, what about deep? You know, deep is the same, but the number of layers is bigger. So we can use here not one layer, but for example, 3, 4, or 5 layers. It depends on your task and it depends on your data. You know, when you train some data, for example, and you want to use 5 layers, I wanted to make a big, deep system. You know how many parameters should have your system, will have your system if you use, for example, 5 layers. Today we will build our deep system, I think 3 layers encoding, 3 layers encoding. The number of parameters is equal to 200,000. So I said correctly, I think. So we should use the number of training data that is almost equal to number of our parameters, because if didn't touch nothing, I don't know what's happened. The number of data and number of parameters should be equal one to another, or maybe number of parameters should be less than number of data. So if you want to build 5 layers, okay, no problem, find database for training this system. If you will find your data, for example, with, I don't know, 10,000 objects, and the number of your parameters became 1 million. Nothing happens. It will be, this system can be trained, can be learned. And also, deep autoencoders often used for tasks of, for example, for supervised learning system or unsupervised learning system, like pre-training models. So do not start from random parameters, because as you understand, if you have such number of parameters and all of them are random, our learning will be for years, yeah, I think. So this deep system that was built, I think, for example, 5 years ago, it's like 2015 maybe, few months this system was trained, and right now we can build deep learning system like we will do today. And in my workshop, I just at first I will start learning, then we will discuss something about deep pre-processing, and when we finish our discussion, I think it's close to 45 minutes, our system will train its parameter, and then we will see the result. I wanted to pre-train it at home, but right now I'm trying to train it here, and you in your computers also can try to build it here, or maybe to download these files at home and train, all will be okay. You all have the special files from me, it's like readme.txt, you have such information, I think. about some pre-training steps you should do before loading my data, because you have installed special environment in your Anaconda. You should install Python 3.6, because in later versions it doesn't work, because some methods work a little bit different, and so it's really important to install all these that contain readme txt, and then all became super. Okay, so about deep auto-encoders also, we should have enough data, we should have enough time for its training. But it's not months, it's about minutes, maybe hours. It depends on your computer, on your laptop. Here, I think in this computer, we just try to install it, to run it. It's like 45 minutes. But in a laptop, it's a little bit other. I think in not really powerful laptops, it can make some hours maybe. But I don't know what computers you have here, so it's maybe better to start my workshop in a computer that is in this laboratory. Okay. Also, deep model system can be overfit. I show you some procedure to make this overfitting less. It's like about sparsing. Okay, what about application? At first, it's medical image analysis. Yeah, of course, because some deep systems are used for image analysis. It can be removing noise, it can be filtering, it may be animal detection, like it will be in our workshop. And also it's about feature extraction task. So you can extract some information using auto-encoder. Anomaly detection, I said, but it's about tabular data and about time series. It's really important. It will be different structures, but it's possible to do. And also for deep neural network pre-training. Okay, so let's start a little bit, be close to our workshop. How to process tabular data? Okay, I said possible. You can see here, maybe not a good quality, but here I can see good. It's like a little workflow for this. How we can make it step by step. We have some data set. And this data set at first should be pre-processed. It can be some outlier detection, some maybe pre-processing our data, but by some ways it can be, for example, if we're talking about natural language processing, it can be word embedding, so some pre-processing always needed. And then became a big feature extraction. And today at workshop I'll show you some pictures that I made by principal component analysis, and I compress the space of 9. I think the dimensionality of space was 9 features to 3-dimensional space. To make visualization, for example. Is it possible? Yeah, please. You can see how each data depends and what is the distance between data. Is data forms some clusters? We will talk about this picture a little bit later. And I do it also by autoencoder, simple autoencoder, maybe 10 seconds. It's like training, simple architecture, and we have a data and like also 3 features. Is this picture the same? No. What picture is better? the answer for this question will be after feature learning system when you use some supervised learning system. For example, I don't know, random forest model, for example. You took information not from output layer or from input layer. You took it from bottleneck. So, why it's really important that autoencoder be a part of some system. For example, it's really important for medical workers, for physicians, for doctors who want to process such data. Because the first question you have in this situation, what is measurement to this axis? For example, principal component 1. Is it height? Is it weight? Is it feature 1, feature 2? What feature is it? And you can't answer this question because it's like combination of all features. It's like if you want to do not answer this question, autoencoder should be a part of your supervised learning system. So you see features like input of your data, it's like here, and then you see the result of this system. And if the result is good, nobody wants to know what is inside, how this data moves through your system, how it's like some calculations and that's all. Because nobody saw this layer, this bottleneck, and nobody asked question, what is this layer, what is measurement for each data? I don't know, it's like, why number 3, why not 4? I want 4. It's like, it's a question that some person shouldn't know, yeah? Because it should be one system. And then the supervised learning system, when she have it input information from principal component analysis, feature extraction from this method, for example, percentage of training is, for example, 95%, which is like separating on 2 classes. And after autoencoder feature extraction, it will be, for example, 97%. So this representation of reducing 9 features to 3 features is better than reduction, for example, using PCA. Yeah, it's better because the percentage is better. So we should have different methods for extracting information. Yes, of course, is in such data that are simple, we have no need to build autoencoder or maybe deep autoencoder because it's PCA, it's better, it works. We shouldn't use some other system. But sometimes, as you can see at this data, you can see here, like it was like overlapped, yeah? We have overlapped classes here. One class is white, different classes is black, and here is overlapping. It's really complicated to build such system to make this overlapping like linearly separated because PCA or maybe other system, I don't know, it can be a logistical regression, linear regression system, or maybe other, not random forest. Random forest works good in this situation, you know, and different methods are not. So it's how to separate these classes. It's a really difficult task. And here you see the separation, it's not so big. So autoencoder make our data, it's like with bigger distances each from other to separate, to make supervised learning system be able to separate this data on, for example, 2 classes. But it's about tabular data, and what we will do if it will be not tabular data, it will be time series. So it's impossible to do this way, and it's impossible maybe to use, for example, PCA, it's impossible to use at all. Never use PCA to time series, because it mixes information about your time. And when you mix this information, it's other information, other time series, so you should stop. And autoencoder in classical representation you shouldn't use for your time series because also of this problem. So how to use autoencoders to time series? For this, LSTM can help us. LSTM, it's a long short-term memory. It's like a different way of building gated recurrent unit. It's like a recurrent neural network that can work with time series. But, you know, GRU in classical form can remember only information that it saw not a long time ago. It's like short term of remembering. And LSTM can remember information about all the time that information was fed to its input. GRU has two gates. It's like a simple gate. It's like a unit that has some simple operation with data. And GRU has a reset gate and update gate. So it can reset information or maybe update it using such sigmoid function and tangent function here. And that's all. And about LSTM, the number of gates is bigger. It's about forget gate. The principal is cell gate, input and output. Let's see how it works, because we will use our LSTM inside of our deep autoencoder to make prediction for our time series. And I will show you how. So let's talk in a little bit. You see some animation here to make the work of this LSTM without formulas. Yeah. So you see, here we have hidden layer of previous layer of our network, and here we have input information. And this is a forget gate. This gate, what does it do? It decides what information should be kept and what information should be thrown. And decided to use it using a sigmoid function. If the value at the output of this function is equal or close to 0, this information will be thrown. If the if the value of sigmoid function in output of our system will be equal or close to 1, this information will be kept. So, for this, we use the layer, previous layer. Here you can see this part of LSTM. It became the input layer for other layer of LSTM. And input information. Okay. Then it's about input gate. Input gate is this part of our LSTM. And here we can see two activate functions, sigmoid function and tangent function. The form of these functions are almost the same, but we have different limits for sigmoid function. It's from 0 to 1. From tangent function, it's about -1 to 1. So here you can see that the previous hidden state and the current input are passed to a sigmoid function, and this function decides which value will be updated by transforming it from 0 to 1. 0, it's not important information, 1, it's important information, like at previous step. The hidden state and current state are fit to tangent function, and it also, the values became from -1 to 1. So, here we will multiply these two values, and sigmoid output will decide which information is important to keep from tangent output. So it's like a coefficient for this output. Then we will have, it's about cell state. It's like important cell state. It's like all information goes from our LSTM by this way. So here you can see the previous cell state, and here you can see the our forget. Yeah, if we should forget this part or maybe not, it depends on this multiplier. Then we will summarize it with, or it will be added block, yeah, added block, with some new information from our input. Is it will be necessary, is it will be important for us, depends on, as you remember from this sigmoid function. And then here we have output of our LSTM. So some information can influence to our output and some not. And the last layer is output layer. It forms by these two functions. Here we have the same, our previous hidden layer, and here we have our input. This sigmoid function decides is it important or not. And here we can have information about our cell state. We use tangent function for make it with positive sign or maybe with negative sign. We are maybe close to 0 or to 1 or to -1. It depends on situation. Then we multiply these two signals and we have hidden signal for our next layer of LSTM. We will use, it's the end of my lecture. We will use these blocks inside our deep system. How we will use it? I'll show in my workshop. And right now, I think we have a little Q&A session. If you have some questions, please. Thank you.
Thank you again, Iryna. So now it looks like we don't have any break, so we should just continue with
We can continue, yeah?
But if somebody has any questions, please don't hesitate to contact Iryna. Right now we can have a few questions, I think, and then afterwards also. So up to you, please.
Okay. Does anybody want to ask something? Or maybe we will discuss it in a coffee break, I don't know, as you want. Okay, maybe coffee break. Okay, let's continue. So right now we start our We'll start our workshop, and for this, tell me please, are you want to, it's like, I want to see how it's shown here. Can you see the text? It's really important. Yeah, it's possible, okay. I'm not sure that I can, okay, we will do it by this way. Okay. Give me 1 minute, please. I try to see if it's possible to make like this. Is it possible to make like this? No. Oh. I want to switch between windows, and trying to do something. Oh, yeah, okay. The goal of our workshop is to see how we can visualize our data and how we can make anomaly detection in medical data based on our deep auto-encoder. This workshop should be made by Iryna Perova, also professor at our university, but unfortunately she can't present it, so I'll do it with pleasure. Okay, and what is our agenda? It's how to process tabular data, how to process time series, and here we can see our LSTM. And we will build two auto-encoders, one for tabular data and one for time series. And we will start, I think, for tabular data. This tabular data is presented by breast cancer Wisconsin data. All who make ever in their lives data processing know this known data set from UCI repository. It's about this data set describes the images of mammogram by arranging some features like cell size, say color, say and other information about images, about mammograms. This data set use, I think, 9 features, and one feature like diagnosis. Is this picture contain some information about breast cancer or not? And we will use this data set for make image in three-dimensional space using autoencoder and using PCA to see. You saw it in my lecture before, and I show how we can do it. So at first we import in some modules, just import it. And then we load our data set using some, I think it became better to see here, okay. We import this data set using some separator, because this data was at CSV file, separator was comma, and there are no header. And maybe I'm not sure, but I can show you maybe this here. And you see some array with some features. That's all. It's like NumPy array here. Then we should normalize our data. Normalizing depends on such way you use. For example, when I build PCA method in MATLAB, principal component analysis has normalization layer inside. So you have no need to normalize data. In Python, it's not. So before using PCA in Python, you should normalize your data. It's necessary to do because it's necessary to do. Okay, we use a min-max scalar for normalizing. We feed it to our data set, then we transform our data set to data set. So we do this action, and then we use the method train test split to separate our data to training set and to testing set. It's known, right? So to build principal component analysis, you should import it from sklearn decomposition. And then we can create our own PCA by using 3 components from our PCA, and then we can feed it to our data and then create data frame, for example, from 3 of them. When you calculate principal components, it's really important. You change your space, and the total dimensionality of your space became the same like your initial dimensionality. So if we have 9 features, we will have 9 principal components. It's normal. But we know that these components are arranged, so we can use first because this component has the most part of information. Second, we'll have a little less number of this information, and that's all. So we decided to take only 3 components because we will use it for visualization, and we want to do it in our normal by normal way, like for our life, we are living in three-dimensional space. And when we do it, we have this picture. You saw it in my lecture, but it was a little bit compressed, yeah, because it was a little bit smaller than here. And here we see one cluster and other cluster. Okay, we represent 9-dimensional space using 3-dimensional space. It's about feature extraction. Then I want to create some dense autoencoder using Keras model, like creating some layers for this. And we will do it like we will have input information with some numbers of features. And we have 2 layers with 64 nodes and with 16 nodes with different activation functions. Here I decided to use sigmoid function. And we have some information to this layer that has name encoded 1. Is fed information from input I, and we show it here. Then to level, for example, encoded 2 is fed information from encoded 1. So we build our system layer by layer. And then it was encoder part. You see only two layers, yeah? And only 3 layers, sorry, because it's a bottleneck here. Yeah? Here we have some dimensional reduction. And then we try to decode our data to make our renovation, or maybe it's like decode our information by better way. So the number of nodes will be the same, like at previous step, the same activation functions. Here we see what layer, how our layers are connected with each other. And here we see our decoded layer. And then here we build our model to encoder and to decoder with input and output information, and our autoencoder was built using it. It's like a function here. This function returns us encoder, decoder, and this model of our autoencoder at all. So then we will use it for our data, and we can see here we call our function with parameters by the default. Here we have no tuned parameters, so here is simple autoencoder. And then we can use 2 methods for regularizing their parameters. The method RMS_prop, it's built inside Python, so you can call it. We just imported it before. And here we have some parameters for this regularizing method. It's epsilon, momentum, blah, 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 different parameters. So if you want to use this autoencoder by yourself to make it, you should find what parameters will be better for you or not. So it depends, this parameter depends on your data. All of these parameters has their value by default. So you can at first use value by default, and then to try to change, maybe it became better, maybe not. So you should understand this parameter not from my speech here right now. You should understand it by your hands. You should try it by yourself. And also Autumn regularization parameter, it's not parameter method, it's a known method for regularizing deep neural networks. And this also we have such different parameters for this method. When you ask Google to show you Autumn regularization, you see the formula, and this formula contains beta 1, beta 2, and you can choose. You can see what values it should be and to tune your autoencoder, for example, by Adam. I use Adam here with a last function, as I said, there are some different loss functions. Here we can, I will use mean square law function. Then I said, okay, let's summarize my autoencoder and fit it to my X train and here you see, not Y train, because I should renovate my information from X train and make it close to X train. It's like encoding, decoding. It's not like a supervised learning system when they use, for example, data and then diagnosis, yeah, for like a goal function that should be. Here we use our data in input and our data in output. We want to use some epochs, number of epochs to learn our autoencoder, and some batch sizes. We shouldn't shuffle our data, but we could if we want to do it. But our data here in this data set, the data are shuffled before, so I know it. I know it, and I set shuffle on false. And some validation data. What's validation data? I should understand if it was good or not. So the part of my data was X test. So I use it for validation. And I want to build this model. And you see, blah, 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 50 epochs. It's like close to 1 second or maybe less than 1 second, and all is done. My autoencoder is trained right now. And as I show you, we have some picture of working of this autoencoder, and we see different information from PCA and from autoencoder. So we can use all this information. Here we use it for building from encoded data. You see, we use 3 features to build our picture here, but you can use it for classification, for input of supervised learning system, and to train your system based on this data. Because this data characterize all breast cancer CSV data set at the best way, as you can see here. Because we see that we can almost separate 2 clusters, 2 classes, one of other, and we can build such system. Maybe it will be some, not 100%, but I can say you that if you use random forest model here, it will be close to 100%, maybe 97, 98, but it will be good classification. Okay, it's about tabular data. Only I wanted to show you how I got these pictures in my lecture. And now we started for deep autoencoder, and I don't want to show you code because right now I'm asking you to open all you have in your computer. You have Jupyter notebook, I think it's opened, and here you should find on your desktop the folder for participant, and there you should find the file autoencoder stud, like this name, but also student, for students. And I want to say you it's about LSTM. Okay, and if you use your own laptop, please, you should activate your environment. Are there somebody who use not for gaming? Can you activate you should open Anaconda, I don't know, maybe who use Mac, you should open CSV, or you should open a terminal. If you use a Windows system, you should open Anaconda prompt and print there, Conda activate my env. Your env should be pre-installed, so please do it. And then print there Jupyter notebook, like in my readme txt, and open the file.
It's here in your you have?
It should be here, yeah. It's open right now. You not close. You just. I can hear you. Sorry. Okay. You can see it's open here in your browser. It's Jupyter notebook. No, not close, not close. Yeah. Here, desktop and for participants folder. And here, auto-encoders start. Yeah. Is it works? Is it okay? Can you find your?
Если все сделал, как было написано, что дальше?
Have you opened your file? Okay. What you did? You just. So what you print there?
Everything that's written this guideline.
Okay. Can you print? Activate my env. So you will activate your environment and then please print Jupyter notebook.
Where?
And well, what? Okay, so it's okay. I'll show you what you should do. 1 second. Who have questions for loading your file for work? Okay. Yeah, my env, yeah. Okay, you see, your env is activated. So, Jupyter notebook, please print Jupyter notebook. Okay. At first, I want to tell you about our time series. I find such interesting information in the paper Does Machine Learning Know When I'm Scared? So, what about scared? It's like some anomaly in time series. It's not a normal process. So, we use this data for anomaly detection. For this, I took the data from Fitbit smartwatch. This smartwatch can measure heart rate and calories that you, and this measurement you can do in your normal life all the time. And at this paper, the author said that if you have this Fitbit smartwatch, you can register, login in this site, and all information was there in cloud, and you can use your personal information for training your personal auto-encoder. But I have no Fitbit, I'm sorry, I have Apple Watch, and Apple doesn't help me to download some information from my smartwatch. So I find some data from Fitbit and also Google Form PNC's different types of smartwatch. You can use this link for downloading it 1.4 gigabytes for this data set. It's big data set that contains information about, I think, 16 persons here during 5 months. So you can download it and use different data to see if our auto-encoder works good or not, because I use only one person. And right now, it's really important to me to make like this, and I'll show you a little bit later what is this, because I wanted to start learning of my model. And here you can see, you will see how it starts, maybe right now steps like make one after other, and we will discuss the steps when my model became better. And here you can see the time, because we're talking about a big shape of data. So I have a really powerful laptop with i7 processor, and you see what, oh, here is my model, and you see first epoch from 15 I think it should be 45 minutes. You see, one epoch, it's like 3.20 seconds, something like this. And you see some parameters, so we will go up and we will discuss how to build it.